Hello, thank you very much for joining me today. My name is Max Hoedel. I am a PhD student at TU Munich, working at the chair for Photogrammetry and remote sensing under the direction of Professor Uwe Stilla in cooperation with BMW of Munich, Germany, working on a project regarding inline photogrammetric surface inspection in automotive production. Today I'm going to be talking about current and future strategies as well as the details of our PhD project. Now, before we begin, I'm going to go ahead and switch off the webcam to keep the slides clean. I will turn it back on and see you again on the other side. So to begin, why do we need photogrammetric surface quality control? Well, plain and simple, automobile manufacturers, especially premium manufacturers, need to ensure flawless vehicle exteriors to keep customers satisfied. And press shop production, where the components are made out of blanks of sheet metal, is a very error-prone process. There are many complicating factors that can lead to systematic and non-systematic errors, and in order to detect all defects, a 100% inline inspection is needed. On the right, we see here a diagram of general press shop production worldwide. And for the most part, components are produced and some of them are taken off the line at regular intervals and inspected in a sensor room. However, this is not satisfactory for Industry 4.0 requirements, which is why we need to migrate to something that is akin to what is shown on the bottom of the diagram, where at the end of the press line there is a sensor system installed which measures every single component that is produced, giving a comprehensive quality metric of each component, or a series of quality metrics. And photogrammetry can aid us to this end because it enables contactless full-form inspection. So this transition from at-line to inline is our main motivation for researching such a photogrammetric surface quality inspection system. So what are the primary challenges for inspection? Here we have three groups of primary challenges. The first of which is the industrial group of challenges, meaning the challenges that arise from the very complex production environment that is the press shop. These can be vibrations, since we're moving hundreds of tons of steel at millions of pounds of force up and down. These can be lighting variations depending on the time of day, depending on the lighting within the factory, and these can be things like conveyor belt movement. Since we do produce components every couple of seconds, they are moving at a meter per second to 2 meters per second, so we don't have the luxury of having a static component and ample time to measure. The second group of challenges is that of material challenges. Since we use different types of steel and aluminium, we're dealing with different degrees of specularity, which is the degree of reflectance off of any type of metal. This can complicate inspection, as we will see briefly. Also, the components are oiled before they enter the press line, and this oiling is not always entirely homogeneous, so this can also be a challenge for photogrammetric inspection. And lastly, regarding material challenges, modern automotive production does entail the production of very complex geometric components. Anything from a fender to an entire sidewall can be punched out of one blank, which means we have a lot of different radii, a lot of different surface normals, edges, etc. The final group is that of data processing challenges. So the type of sensor, the type of data that that sensor puts out, as well as the time to measure for our different sensor technologies, and the problem of finding an ideal resolution, where we want to find the minimum resolution that can entail all of the quality data that we need, but no superfluous data that is only going to fill up our clouds, but not help us regarding data-driven production. So since we're now familiar with the challenges that are posed by press shop production, we can take a look at the spectrum of surface defects that we will be looking for. This is a non-exhaustive list, but these 6 defects shown here on the right are the primary defects that can occur, which are associated with the highest reworking costs and reworking minutes. Now we can subdivide this list into 2 primary categories. Those categories being systematic defects like bulges, dents, and waviness, which can occur due to irregularities in the pressing tools themselves, as well as irregularities in the pressures and amount of oil. And we also have non-systematic defects, such as scratches, pimples, and notches. So with pimples, for example, we could have dirt that flies into the press and gets in between the tool and the steel, or a notch is akin to a pimple, but it occurs when metal flake flies into the tool and then gets stamped into the component, or scratches where perhaps we have a local amount of oil that is too low, causing the metal to be dragged across the tool without significant lubrication, causing such scratches. And a further differentiation can be seen in the geometric presence of these different defects. Now, what do I mean by that? What I mean is that a bulge and a dent and waviness can be seen in the geometry. We have to delineate between geometric defects and surface defects, but these systematic defects can almost be seen as microgeometric variations, whereas the defects on the right really have no geometric presence, or none that can be seen with legacy sensors, but they can be seen in image space, just as you can see them right now on the presentation slide. And that will remain relevant as we begin to discuss the different technologies that we have to our disposal to detect all of these defects. The first of these technologies, and indeed the oldest of the technologies that I'll be discussing today, is that of laser line triangulation. Now, laser line triangulation is not to be conflated with polar laser scanning, because in polar laser scanning, I'm measuring angles and distances, whereas with laser line triangulation, I project a laser line, as the name implies, onto the components. I observe that laser line from an offset camera, and any surface deviation will register as a deviation of the image of the line on our sensor. So when we take the issue of specularity into account, we come to the conclusion that we need a diffuse surface for laser line triangulation. Though a quick disclaimer, there is research ongoing into specular laser line triangulation, but the legacy sensors that exist need a diffuse surface in order to be able to clearly see the projection of the laser line. Regarding cycle times, which is another main restricting factor, laser line triangulation requires mid to long cycle times because I have to sweep the line across the component and do a continuous acquisition, as opposed to, say, the full frame acquisition that can be done by photogrammetry. The second technology, and indeed a mainstay in automotive production worldwide, is that of fringe projection. With fringe projection, a usually sinusoidal pattern is projected forwards onto a component. That pattern is then acquired by a camera. In some cases, it is then phase shifted, but in simple terms, the phase of the pattern is encoded in the intensity, which allows us to triangulate forwards onto every part of a given surface. This also requires a diffuse surface in order to be able to clearly see the lines. However, again, as with the previous technology, I should mention that there is research ongoing into specular fringe projection systems that use laser projectors that have an incredibly high intensity, thus allowing for a clear triangulation onto specular surfaces. Requiring cycle times, we are also dealing with mid to long cycle times, since phase shifting is generally conducted in order to cope with discontinuities in our surface. Although single acquisition fringe projection can be done, if there is, for example, a CAD model that can be used to figure out where discontinuities are. But for the most part, when we talk about fringe projection, we are dealing with phase-shifted fringe projection, which requires these mid to long cycle times. The third technology, and the newest of the three legacy technologies that I am showing here, is that of deflectometry. And there are different subcategories of deflectometry, but normally we are referring to phase measuring deflectometry. Now, phase deflectometry or phase measuring deflectometry can be viewed as a sort of conceptual inversion of fringe projection. What does that mean? It means instead of projecting a fringe pattern onto a component, I am reflecting a fringe pattern off of said component. So I have a screen with a pattern shown here top left in the diagram. That is then reflected off of a component, and the image of the deformed fringes is acquired by a camera. And in doing so, we can see that if there is any deviation in the surface normal, that will register as a deformation of our fringe patterns. Now, since we are now reflecting and not projecting, our specularity requirements are also inverted, meaning we now need a specular surface. For example, a painted surface. So deflectometry can be used and is used, for example, at BMW for surface defect detection on painted bodies. However, as of yet, it cannot be used reliably on diffuse surfaces. But there is ongoing research into the field of infrared deflectometry, which I will touch on again briefly, where the optical pattern in the visible light spectrum is replaced by a pattern in the infrared spectrum, and that allows for a coherent reflection off of a diffuse surface, enabling deflectometric acquisition of diffuse components. And that will also be a part of ongoing PhD research between myself, TU Munich, and BMW. With regards to cycle times, again, we're dealing with mid to long cycle times, since we do have to conduct phase shifting, again, to deal with discontinuities in the surface. The fourth, final, and indeed most arbitrary group of technologies is what I have deemed camera setups. What do I mean with a camera setup? Well, instead of projecting lasers or fringes, instead of reflecting fringes, all we're doing is taking a camera, taking an image or a series of images of every component, running that through a computer, usually through deep learning, through neural networks, though deterministic approaches can be used as well, and looking for defects that we can see in image space. You might recall I discussed the spectrum of defects earlier and said that some of the non-systematic defects don't have much of a geometric presence in the surface, but they can be seen with the naked eye and thus can also be seen using cameras and deep learning. The biggest advantage here is that we can look at diffuse and specular components or materials, and that our cycle time requirements are very short because, of course, we can just conduct a snapshot in a thousandth of a second, and if we have good GPU acceleration for our deep learning backend, we can quickly derive a quality metric on whether or not a component is okay or not okay. So, having looked at these four technologies, we now look at an aptitude overview of each of them regarding the four main steps of automotive production. Now, to touch on these briefly, we start off in the press shop, where the components are stamped. We move on to the body shop, where the stamped components are welded or epoxied or otherwise joined together. Then, the body, or body in white as it's often called, progresses to the paint shop, and this is where the material goes from being diffuse to being specular. And in final assembly, we install the powertrain and the interior and exterior fittings, and finally ship the car off to the customer. So keeping the issue of specularity in mind, we see that the press shop is the only step of production where there are no available turnkey solutions. Laser scanning is generally too slow. Fringe projection is generally also too slow and susceptible to vibrations. Deflectometry fails because we have a diffuse surface, and camera setups are potentially feasible, but since this is such a new field, there are no turnkey solutions yet available. However, if you go to trade fairs, you do see that companies are starting to pitch AI camera setups, but they have not yet really been proven in our industry. But hopefully that will soon change. Another thing to be noted here is that the rightmost column of camera setups has been deemed from preliminary research to be feasible for all stages of production, primarily owing to the fact that they can be used on specular and diffuse surfaces, as well as the very short acquisition times. So in order to put a green rectangle into the top of our chart here, we have undertaken this PhD project, which will make use of technologies like infrared deflectometry and camera setups, but we will get to that momentarily. So what is our approach? What experiments are we going to do? Well, to begin, we have determined the relative frequency and associated reworking costs associated with each defect type, as was presented earlier on, so we know what defects to focus on. Then we have also installed sensors in our press line to determine the vibrations, so we know what vibrations any potential system will be subjected to. Furthermore, we have procured a set of sample components that have edge case defects. Here you can see a BI6, BI7. That is BMW specific jargon relating to the quality of each component. So BI7 is acceptable, BI6 needs to be reworked. So in order to calibrate our systems correctly, we need to find components with defects that have these edge case defects in them. That has also been done. Then, as just presented, we've determined the aptitude of various technologies and are now planning to create a prototype for comprehensive press shop inspection. So, the next presentation is going to be from Mr. Isaac Dupries from South Africa, who I have been cooperating with over the past year. And he will be showing you a very clever and novel deflectometric system wherein the screen that projects a pattern, or excuse me, that shows a pattern that's reflected, is replaced with an arch, as you can see on the right, with the Mini inside the tunnel arch. And by moving that arch over the car, you can observe the pattern as it progresses across each component, and the latitude, meaning the position on the ring, is encoded in that light code that you can see, and that can then be used to solve a series of partial differential equations, leading to a normal map, leading to the ability to detect defects. However, you may be thinking, well, that's optical deflectometry, right? So that's not going to work in the press shop. And indeed, this is true, which is why the next point on our agenda is going to be to transition that technology to infrared, meaning we're going to replace the light ring you can see with an infrared, with a thermally emissive latitude code. And that is going to be one of the main points of research in the coming year. And furthermore, since I touched on the concept of geometric and non-geometric and systematic and non-systematic defects, we are going to hybridize this technology with camera detection, meaning that the latitude encoded deflectometry will be used to detect things like bulges and dents, and the AI camera-based technology will be used to detect things like scratches and notches and pimples, which may not be detectable using deflectometry. So in order to conclude, we want to deliver a proof of concept for an inline inspection system that is able to detect, classify, and localize all customer relevant defects. We want to expand upon the capabilities of deep learning to this end, using things like generative networks, attention networks, or any other architecture. There is a lot of research in deep learning for surface defect detection going on, and we are going to try many of those different architectures to see which best suit our needs, and then modify and expand upon them as needed. Then, as stated on the last slide, we're going to realize our infrared latitude encoded deflectometry system, which will be the main breakthrough of the PhD project, and something that I very much look forward to following up with you all on. And finally, we want to move press shop production into the world of Industry 4.0 with 100% inspection data, so we can also do things like learn parameter optimizations from production. So if we have, say, 10 dents in a row, we can use machine learning and look at our oiling and pressure settings and then determine correlations, which will allow us to create a more data-driven and sustainable press shop production. I look forward to following up with you and would very much like to see many of you next year, back when we can meet again in person. I am joining you right now from my grandfather's living room, which he was kind enough to lend me. But next time, perhaps in the tower in Bilbao in Spain, might be an even nicer atmosphere. So thanks again so much. Here you can see my name, my email address, as well as the internet site for my chair, which is the Chair for Photogrammetry and Remote Sensing. We have a lot of very interesting research topics going on regarding point clouds, regarding scene reconstruction. So stop by there if you'd like to see what else my chair is doing. Below you see the website for my working group, which is ISPRS Working Group for Vision Metrology. And finally, since BMW is kind enough to sponsor my PhD, I would be remiss not to mention our company website, bmwgroup.de, where you can catch up on all things BMW, careers, research, future strategies, and the like. So thanks again so much, and enjoy the rest of the conference. If you have questions, I look forward to seeing you in the Q&A round. Goodbye.